Okay, I think we are ready. Okay, so today Ozgun from our department is going to tell us about zigzag persistence in topological data analysis. Okay,
Thank
please
you.
take it away.
All right, so let me quickly start with reminding a few things from previous TDA talks in this series, so previous talks. Okay, so there were these simplicial complexes, sequences of simplicial complexes in each other. So it was, a flipration, in other words. So given a flipration like this, a persistence module was created. So look at the homology groups for these fliprations. And this was called a persistent module. And then from there, some barcodes were created. So like, I don't know, something like this. So basically, this was the idea. So today we will generalize this part a little bit to zigzag persistence. But let me first motivate why one would need something like that. Okay, let me give a few examples. So one example is that you could have a multi-flipration, so flipration of flipration. So you could have something like this, for example. Okay, and then maybe all the way up to KMN. So you could have a multi-flipration, and this will give you these persistent modules in this form. Yes. And so on, all the way up to HKMN. Okay, so these were called multi-dimensional persistence. Okay. Another possibility is to have fliprations of the same object from different perspectives. So, like, let's say you have an object that looks like this. Let's say this is X. Now, one thing you can do is you can filter this object in this direction. So let's say this is T0, T1, and then T2, T3, T4, and so on. So you look at things that stay on the left-hand side of these vertical lines and consider that as a flipration, then what kind of a barcode do you get? Well, for H0, it starts here, goes on forever, and then for H1, you start to have barcodes start here, and then another one starts somewhere over here, and they go to infinity. So this will give some information about the topology of X, but for example, you will not be able to separate this object from this object, or you will not be able to separate it from this object. Right? They will give the same flipration. If you use the same direction, it will create the same barcode, and you will not be able to separate them. But if you use, for example, another direction, and say, okay, let's say you have T1 and then you have T2 and then you have T3, then H0 starts here, and then H1 and the two barcodes for H1 starts at the same point. So it's a different barcode, and if you look at the same direction, it will tell you that X is not this, right? Or X is not this. It will tell you exactly the shape of the object. And if you look at all directions, in fact, look at consider more directions. You can in fact say X is not some shape like this. You can in fact say it's a rectangle, it's not a circle. Okay, this is called persistence homology transform. Okay, looking at different directions. So one thing I want to say here is, well, so to look at all possible directions, you look at, for example, S1, right? That's like a parameterization of directions, and you go to these persistent modules and so on. So this would give a complete picture of the shape, but S1 is an infinite object. So maybe what you might want to do is to consider like a finite thing. So for example, you could consider two directions. Okay. And then let's say this gives you some F0, F1, and this gives you some K0, K1, Now, what you can put in the middle is you can put, for example, their union. And somehow the homology modules you will get will be going in zigzags. So one is going this way, one is going this way, and then you have HF1 going like this, and so on, okay? So you start to get zigzags in the diagram. So to understand different directions and the relations between directions, you start to get zigzags. Yes? Yeah, sure. You assume that X is in it's some definable object in Euclidean space, yes. Whatever definable means. In general, you look at Sn, yes. I mean, you might have something in Rn, and then, okay, well, you will have to look at Sn minus 1, I guess, in Rn. Mm-hmm. No, this is like a filtration you get in this direction. This is like a filtration you get in this direction. And then you take the unions of the filtrations to compare this filtration to this filtration in some way. Right, like it's just you said put it in the middle. Just So like, okay, if you have this, you can take the union of the two. So you have this and this. You see? Like the union of the two separations. It doesn't correspond to a direction. Yes, it doesn't correspond to a direction. Yeah, sure. Mm-hmm. Okay. Now, another thing is, but it gives you an opportunity to compare directions to each other. Because like this filtration, when you don't have a natural map from this filtration to this filtration, but if you put them both in the union, you have a natural map to the union. Or you could have something like this. You could have an object that looks like this, a sphere, and then you can, for example, just divide this sphere into some cylinders. So just, let's say the union is this, and let's say the intersection, so this is let's say K1, K2, K3, K4. Now, there is no natural map from K2 to K3 or K3 to K2, but what you can do is you can, for example, take their intersection, and now there is a natural map from the intersection to K2 and K3. So this will tell you how to compare this homology to this homology. So you start to get zigzags again. So although there's no natural map from K2 to K3, you can still compare them with their intersections. Okay, so the motivating zigzags, let's start to discuss these in a more rigorous way. Okay, so from now on, F is a field, and then I will consider this as the category of finite dimensional vector spaces over F. And then P is a poset would mean P is a category such that for every x, y, and P, the number of elements in the morphism set from x to y is less than or equal to 1, and for every x, y, and P, if the number of elements in x, y is equal to 1 and the number of elements in y, x is 1, then x is equal to y. Okay. Now, so here, instead of xy is a morphism in P, I will simply write x less than or equal to y. And then V is a P module would mean V is just a functor from P to F vector spaces. And then now, okay, here, let me give an example. Okay, from time to time, I will come back to this example. Let me call this diamond N. Okay, so let's say P is something like direction A1, A2, A3, A4, something like this. And then we can go to Fn to Fn. Well, let's go to identity here, and then identity here, and then maybe some map F and identity here, and then F sends, for example, x1, x2, xn to x2, x3, xn 0, something like this. Okay. So this is like an example of a P module. of course, this is a subcategory in the F-vector spaces. Now, what's an interval? I is an interval in T. Yes, what does this mean? This means I is a non-empty full subcategory of P. And then given any two elements in I and given an object in P, if Z is in between X and Y, then Z is also in this interval category, and I is connected. So an interval in the poset would just mean some full subcategory that satisfies these conditions. No, I mean, well, I will just define intervals like this. All right, now, okay, now some examples, for example, here, let's call this the diamond. Well, in this the diamond, I have A2, A1, and then A4 is an interval. Okay, so that's an example of interval. It doesn't matter if they go in the opposite directions. We still call it an interval. Okay, now from now on, assume tau is a poset whose underlying graph undirected graph, I should say, is isomorphic to this Dynkin diagram, AN. Let's say have this. So n many vertices and n minus 1 many edges. All through the talk, tau will mean just a poset that has this structure, where n is a positive integer, of course. Now, as an example, I could have something like this. Okay, it doesn't matter how many times you go in one direction or the other. So these kind of things we will call zigzags, even though you have 3 things or 2 things here. Doesn't matter. All right, so now one example. I will call this the example triangle. Well, I'm giving names to these examples because I'll come back to these two later on. So this will be something like this. And this, let's say, P module triangle equal to this, and then I have, let's say B, here I will send x to A, y to 0, and then here I will send x to 0, y to B. Okay, so whenever I say examples triangle, it will mean this poset sent to this diagram of representations. Now, and this I will call G1, this I will call F2. There will be a reason why this is not G2. This is F2, this is G1. So it will be more clear later on why I'm choosing a notation like that. Now, one fact is that there exists a unique interval between any object of tau. So given any interval, or given any two objects in tau, there exists unique interval I such that I is minimal among intervals in tau that contain both x and y. So notation, let's call this, well, denote this unique interval by I, x, y. So for example, here, in example triangle, I, A1, A2 is just this A1, A2, and I, A1, A3 is the whole thing. Okay. In the example triangle. Okay, now a definition. So we will define some modules over these intervals. So for x, y in tau, we define the module I, x, y from tau to f licht by sending A to f if A is in the interval, this unique interval that connects x, y, and 0 otherwise. And it sends AB to identity on f if A, B are both in this interval, and to the zeromorphism otherwise. So you have these interval modules. Tau is a poset whose underlying undirected graph is isomorphic to AN. It's any of those. It could be something like this. It could be something like this. So, right. Sorry. It is. It's a zigzag. Right. It's a zigzag. Right. Exactly. All right. Posets are finite. Yes, I'm assuming posets are finite. Maybe I should have said that. So whenever I say poset, it's finite. Yeah, sure. Okay, now theorem of Krull-Mark-Schmidt. So every tau module is isomorphic to a direct sum of these indecomposable T modules so this decomposition is unique up to isomorphism and ordering of summands. So one reminder, in example star, for example, I have this f a f x plus y to f b. Okay, here I had fx plus fy. Instead of that, I'm putting fx plus y. It's isomorphic to this interval module from A1 to A3. Well, okay, this is a submodule of V. Let's call this triangle. Submodule of V triangle, but not a summand. So it's although it's a submodule, it's not a summand. So what's the unique decomposition of V triangle? So here, V triangle is actually isomorphic to this interval module from A1 to A2 plus this interval module from A2 to A3. So this is like fx, fa, and then 0, and this is like 0, sorry, this was A, this was x, fy, fb. Okay, so you put f's in the interval, you put zeros outside of the interval. When you take their direct sum, you get this V triangle. And then now, theorem of Gabriel will say that indecomposable T modules are exactly these interval modules. So the indecomposable T modules are precisely the interval modules. So each interval module can be considered as a barcode, just one of the bars in the barcode from X to Y. So you can basically write every persistent module as like a barcode. So here you will have this A1, A2, A3. So you can consider this like a barcode. So having these decompositions, and Gabriel's theorem is saying there are finitely many of these possible indecomposable modules. They are exactly the interval ones, and there are finitely many intervals. So you always get these finite barcodes for zigzag modules. Of course, up to multiplicity, you have infinitely many, but if you forget multiplicity, you have finitely many types. Now, how can we obtain this? So an algorithm to compute these barcodes. Find the interval decomposition of tau modules. So this algorithm is due to Carlson and Silva. So let V be a tau module. Then we will depict V as follows. So V1, P1, P2, Pn minus 1 Vn. So since we don't know which direction the arrow goes, we just put an arrow like this. It would mean it goes in the direction of the morphism in the poset. So here we consider okay, let's say let's say Vi, Pi, Vi plus 1 is Vi F either Vi Fi, Vi plus 1, or Vi Gi, Vi plus 1. So whenever it's forward, I write F. Whenever it's backward, I write G. So this notation would either mean Fi or Gi, depending on the direction. Now, start with the following. So start R01, R11 to be 0V1, and B11 to be just 1. And then in the recursive step, say R0k plus 1 all the way up to Rk plus 1, is Fk R0k, Fk R1k, Fk Rkk, and then Vk plus 1. If Pi is Fi, P sub k is Fk. So if it's a forward map, you define the next step like this. If it's a backward map, you put 0 here, and then you take G inverse k R0k, G inverse k R1k, and G inverse Rkk. So you define like this. And then how do you define these B's? Now you define B1 k plus 1 to B k plus 1 k plus 1 as B1k all the way up to BKk k plus 1 if Pk is Fk, and you define it as k plus 1 k bkk if bk is bk. So you recursively define ri's and bi's. So let's go over the example. Okay, let's discuss this on the example triangle. Now, I remember I had fa fx plus fy, and then I had fb. So here x was going to a, y was going to 0, and then here x was going to 0, y was going to b. Okay, now we start with R0, 1, R1, 1. Yes, this is 0, V1. Of course, this is V1, this is V2, this is V3. So it's just 0 FA. Now, what is R20, R12, R22? So the first map is a backward map. So we're going to use this formula. So this will be 0 G1 inverse R01. So let's say 0 G1 inverse FA. So this will be 0. Here, this will be Fy. This will be Fx plus Fy. So you can see that this is a filtration of Fa, this is a filtration of Fx plus Fy. And then F30, F R13, R23, R33. Okay, now this is a forward map, so we're going to use this formula, and that will be just F10, F1, Fy, F1, sorry, this is F2, I should say, F2, Fx plus y, and of course Fb. So basically this is 0, Fb, Fb, Fb. Okay, now what? Now you're going to find where the b's fit in the last sequence of b's. So the last sequence of b's is b1. Well, in this case, it will be b3. Or let me say it in general. So you will look at bn bnn, and you will find where bk fits in. So there will be a unique place where this bk's will fit in. And then you write the row, just underneath it, you write the row R1k over R0k, and then RKK divided by RKK minus 1. And then when you look at these things, it will give you the barcode. Okay, let me continue with the example triangle. So for example, in this case, let's also calculate the b's. Sorry, b12 is what? So b1 to b22. Yes, the first map is a G. So you put k plus 1 here, so this is 2, 1. And b31, b23, B33 is 213 because the next map is a F and you put K plus 1 over here, so you put 3 here. Okay, so now you have the last thing is B13, B23, B33, so you put 213. Now, how does B11 fit in here? It fits exactly here, right? So you put R11 divided by R10 over here. Okay, maybe let me draw this a little bit larger. There's 2, 1, and 3. That's the last B. B13, B23, B33. And then I have B11. So I put R11 divided by R10 here. Well, what is R11 divided by R10? It's just FA divided by F0, so it's just isomorphic to FA. Okay, and then B1, 2, B22 fits in here because it is 2, 1. So you put R 2, 1 divided by R20 here, R2, 2 divided by R12 over here. And what is R12 divided by R02? Well, it will be Fy, and this will be Fxy divided by y, so it's Fx. And then you put the last thing, B13, B23, B33. And then here you have R13 divided by R03. This will be just FB, and then the rest will be just 0. So basically, you can see that under this column, you have this interval, and under this column, you have this interval. So it's the two intervals that we draw. So of course, here, A1, A2, A3. So the rows, the columns will give you bars, the rows will give you the intervals. So it's exactly this decomposition that we talked about over here. All right. So there is no theorem like this in case of more general modules. For example, for the diamond, we don't have a theorem like this. So there are infinitely many. In fact, if you look at the diamond, you can increase the n and you will get infinitely many different indecomposable types. So what do we do in that case? Yes, well, what do we do in that case? Well, we use more, we use invariants which are not exactly complete as this one, but still it might help you to differentiate between things. So these are called rank invariants. Let's see. So, okay, what can we do for more general posets? So we talked about tau. Well, answer. Okay, assume P. Well, assume V is a P module. And let's say V is some vector in the direct sum of all these vector spaces when X ranges over objects of P. Then we will say V is called persistent vector if, okay, V, well, if for every morphism xy in P, the image of Vx under this morphism is Vy. Right. So somehow, if the vectors are compatible, we call it a persistent vector. And V will be called fully supported if V is a persistent module, persistent vector, and moreover, for every x in P, Vx is non-zero. So if all the vectors in this, if each component is non-zero, then you say it's fully supported. Okay, let's call LV the submodule that consists of persistent vectors. And let's say this is the submodule spanned by all non-fully supported persistent vectors. Okay. Now, then we can define the rank of V as the dimension of the vector space LV divided by WV. Okay, so now back to example triangle. So what is the rank of V? Well, so here V was actually equal to FA Fx plus Fy to Fb. Now, X was going to A here, and Y was going to B. The rest is going to 0. Okay, now, well, actually, the rank is 0. Well, why? For example, here you could have ax plus y b. So v equals ax plus b is a persistent vector. Why? Because here y is going to 0, x is going to 0. So really x plus y is going to A, x plus y is going to B. So this is a persistent vector. But it is equal to 0 because here A x 0 is in, so both ax0 and 0yb are elements in this non-fully supported persistent vector. So because ax0 is also persistent, 0yb is also persistent, but these are non-fully supported. And the sum of these two is equal to this. So here w1, w2, and v is equal to w1 plus w2. So v is 0 in this module. So the rank of this is 0. But rank of, for example, the interval module, A1, A2, in example example triangle, is 1. And rank of A2, A3 is 1. So from here, we get rank of the interval A1, A3 is 0. Okay. So now we define the rank invariant. Okay, let's say in P denotes the intervals in P. Then we define rank invariant from intervals in P to natural numbers by sending the interval I to the rank of the interval. Okay, let's say rank V to rank of this interval. Okay, of course here V is some P module. Oh, well, I should say V restricted to this interval. This. So if you restrict your V to the interval, so you're just restricting this functor to just this interval, and if you're looking at the rank, then you have this. So for example, here for example triangle, the intervals, there are 3 intervals, this one, and this one, and the rank function just sends these to 0, 1, 1. Okay, now a proposition is let V be interval decomposable then the rank of I is equal to summation over all intervals that contain I of the multiplicities of V of this interval in V. So since it's interval decomposable, each interval has a multiplicity in the decomposition the number of such intervals is determined by Kuhl-Schmidt theorem, and it's unique. Oh, sorry? I less than or equal to j. Oh, yes, thank you. In j, thank you. Yes, well, still j. That's right. So what's the proof? Well, say if this V is direct sum of VI alphas, alpha over some indexing set, then the rank of VI is equal to summation alpha over A of rank VI alpha i's, which is equal to summation alpha A rank VI alpha restricted to I. And basically this is and rank V I alpha restricted to I is equal to 0. Mm-hmm. So interval decomposable means you can write V as a direct sum of interval modules. Mm-hmm.
But J is running over each T.
Mm-hmm. Right.
Yeah, I was trying to apply this formula to the example, and
I will apply it to the example.
I thought maybe J is not holding to.
Well, it's the intervals that are above I. Maybe I will come back to example triangle. Okay, I will apply it to example triangle. Okay. Yes. So here, this is 0, 1 if I alpha contains I, and sorry, 1 if this, otherwise 0. Okay, now, so the theorem is rank function on T modules completely determine barcodes. So rank invariant is a complete invariant for T modules. So what's the proof? Well, so this is a poset. The poset by the subcategory inclusion of intervals in each other. And then you can put a total order on, you can find a total order on this interval poset, which agrees with partial order, which is compatible with partial order. And we can form M, the adjacency matrix, associated with the directed graph. So this time I'm looking at the directed graph, not the undirected graph. obtained from P, or obtained from in P. Then, well, M is upper triangular, and all diagonal entries are 1. So M is invertible. M is invertible. Now let's call M the multiplicities of intervals. So this is a column vector ordered according to this total order. And let's say R is the rank. Invariant, again, column vector. Now, this proposition star is saying what? Proposition star is saying R is equal to M times this M. Right? When you multiply the multiplicities with this adjacency matrix, you get rank. But now, let's call this mu I j's, then M is equal to M inverse R, and that's like this ij, mu ij. Well, it's basically the Möbius inversion of the posets. Okay, now let's go back to example triangle and let's see what all this means in that example. So I had A1, A2, A3. Now I have the intervals A1, A2, A1. So the interval posets A2, A3, and A1, A3. So this will be the total order I put on the interval poset, because this agrees with the partial order, because this is a subcategory of this one, this is a subcategory of this one. There's no relation between these two, but I put a total order even though there's no relation between these two. So I get the matrix M1, 0, 1, 0, 1, 1, 0, 0, 1. So the diagonal entries are 1. You have an upper triangular matrix. Okay, and then this rank multiplicity is saying I have R is equal to what? Well, it's 1, 1 over here, and then 0 over here. So it's 1, 1, 0. And then what is M? Remember the decomposition. It was, again, 1, 1, 0. It was 1 of this interval, 1 of this interval, and 0 of this. So now I have R equal to M times M, right? And M is equal to M inverse R. Well, what is M inverse? 1, 0, minus 1, 0, 1, minus 1, 0, 0, 1. And 1, 1, 0, right? So basically, this is saying it's enough to look at the rank invariant for T modules. For things like diamonds, rank invariant gives you some information, but it's not complete like this. It can never be complete like this. But at least it's some information that can be used to understand those kind of posets. Okay. Well, actually, yeah. Okay, this is all I want to say. Mm-hmm.
Questions?
Who? It talks about these probability applications. Yes, these are from. So yes, I guess I should also say that all these are from Carlson Silva and Carlson Zomorodian paper, and they talk about applications where they try to understand these probability distributions and things like that. But yeah, I didn't have time to understand exactly what's going on with those applications.
The original persistent
Yeah, they also talk about these diamond shapes, and then they obtain some Meyer-Vickers things. But well, it's somehow helping to compute these things, but it's not really necessary to say that these invariants are complete or there's unique decompositions. Mm-hmm. Well, yes, the first things, for example, I talked about, like you slice the sphere into parts and you look at the intersection of pieces and you get zigzags, for example, or okay, I guess one thing is they look at like dense points, like high density. They get like sub complexes by considering denser and denser spaces. They change another parameter, they get other dense spaces, and then you get like some zigzag type filtrations again from arbitrary data sets, I guess. You can do that, but yeah, I'm not sure. I no, you can get posets, so you can get this rank invariant, right? Mm-hmm. So you can still understand it with intervals because there's no finite type representation set for them. So you can understand it through subintervals of multidimensional complexes. That's actually what Carlson and Zomorodian do. Mm-hmm.
So the last student says that the study of partials is reduced to the study of L models or just for particular partials?
You mean all P modules?
Yeah.
No, but as I said, only rank function is only complete for T modules. So it's a term of Gabriel. The shape of the poset should be either this AN or E something, you know, these Dinkin diagrams. And otherwise, rank invariant is not complete. Only when you have underlying undirected graph in a certain form, you have rank invariant complete. But even for something as simple as this, it's not going to be complete. So, so it's very. What kind of if and only if?
Like the underlying graph.
Yeah. Oh yes, yes. It's Gabriel's theorem. If the underlying graph is one of the Dinkin diagrams in that theorem, then it has a complete invariant, right? It's an if and only if statement, yes.
Any other questions?
Okay,
If not, let's thank Ozgun again.
thank you.